Hello, we're going to do lab number 7, investigation 1 here. And in lab number 6, we determined an invisible force, specifically gravity. And gravity, we find out, is an active force. It's a force between the Earth and an object, and it results, if there are no other forces, in a free fall acceleration. There are other forces as well, other contact forces, and these are referred to oftentimes as passive forces. These are forces which change with respect to forces that are being applied to them. For example, the normal force is a passive force. If you apply 10 newtons of force downward, you're going to get 10 newtons of force back up. If you apply 20 newtons of force downward, you get 20 newtons back up, and so on down the line. Okay. Other passive forces are frictional forces and tension forces. And we will get into that. We'll get into that as we go through the investigation today. Okay. Let's go ahead and get started with friction. Here's how we're going to work out. In investigation 1, we're going to take a look at what effect friction has as far as net forces are concerned. So let's go ahead, page 150, and we see that we have the track already set up. We got a motion sensor on this side. I've got a cart here. It has a weight that's going to drive it. The weight is actually 50 grams. Now, to provide the friction, the cart itself is a low friction cart. To provide the friction, I have this box here, which is called a friction box. And on the bottom of the box is a cork pad. And that cork pad will provide the friction on the surface here. I can increase and decrease the amount of friction by adding masses into the box. And I can just hook up the box right here, and it works out that way. However, what I have to do when I first do my control experiment, I'm going to have the cart and the box moving together. That means a total mass. So in my current control experiment where I don't have any friction, I have to compensate for the mass. And for that, I have added 130 grams into the back of this cart, and that's going to compensate for the mass of the friction box with the masses inside. So let me go ahead and go through this. Activity 1-1, we've got the ramp set up. Number 2, we've got the graphs set up, the velocity, acceleration, and force graphs. Next, zero the force probe with nothing pulling on it. Accelerate the car with a hanging mass of 50 grams. Move your data so that the graphs are persistently displayed on the screen. So we're going to pull this back here. We're going to take the load off to zero out the sensor. And let's go ahead and record what it looks like. And I stopped the recording just before impact. So as we see the applied force, there's our applied force there. Let's go ahead and record that. The applied force is 0.43 newtons. So let me go ahead and write that down. I'll write that down on the whiteboard here. So the force, 0.43 newtons. Okay. Next, what's the acceleration? Well, there's 2 ways of determining the acceleration. I can use the average acceleration, or I can use the slope of the velocity graph. So let me go ahead and use the slope of the velocity graph. In my opinion, that gives us a more precise answer. So we'll just click on that, turn on the line fit, and we get a slope of 0.779 meters per second squared. So the acceleration is 0.779 meters per second squared. Okay, now we're going to turn that on, persistent, so the display will show the old display as well. Let me turn off that and turn off the stats function there. Next question, let's add friction. So I'm going to I've already determined what the friction is going to be needed, so I'm going to take the weight off, or the masses off the cart, attach the friction pad like so, and so we have the total mass remains constant, but this time we have friction in place. We're going to zero the force sensor again. And now let's see what happens. So zero the force sensor. Start recording. Okay, that's good enough for us right now. Take a look at that velocity graph. What does that velocity graph look like? It pretty much looks like a flat line, doesn't it? The velocity graph definitely looks like a constant velocity. The acceleration graph, if I zoom in on that, is very, very close to zero the entire distance. But what about the force applied? We see that there is a force applied of about the same amount. Let me go ahead and do run 2. I'm going to need to bring up the legend for that. So looking at run 2, we see that the force applied is around the same, 0.48. We used 0.43 newtons, so it's a little bit more force is being measured here. Okay, so what does all of this mean? We see that we have a force. Well, let me go back to this. So let's record this. Step number 9, the average force applied to the cart turned out to be 0.49 newtons. But what was the acceleration? The acceleration was 0. So we had a bigger force applied to the cart, and yet we have no acceleration. So question 1-1, if the cart can move at a constant velocity with a force applied to it by the string, is Newton's first law violated? Newton's first law says that an object will maintain constant motion if there is no net force acting on it. Well, we've got a constant motion. We've got constant velocity. So is this a violation? It would be if there was no other forces acting on it. What is causing, but there is another force, it's the force of the cart, or not the cart, it's the force of friction provided by our friction box. Question 1-2. If Newton's first law correctly describes the motion of the cart at a constant velocity, describe the frictional force that must be combined with the force applied by the string. Does the frictional force act in the same direction or opposite direction as the force applied by the string? Let me bring up a whiteboard and we'll discuss that a little bit. So what we have is we have a crate or box. Let's go ahead and here's my cart here. Okay. And what we see is we have an applied force which is going in this direction. So that's the force provided by the string. I'm going to call it F sub S. Next, we see that we have 0 acceleration. So if A is equal to 0, that can't make sense. The only way that can work is if there is a force which is countering that. And so we must have a force that's going in this direction, and we're going to call that friction. There's our frictional force right there. Okay, so the question becomes, does this frictional force act in the same direction or the opposite direction? It has to be in the opposite direction because according to Newton's second law, we see that our net force must be equal to the mass of the object times its acceleration. If the acceleration is 0, then the net force must be 0. That means that the force applied by the string must be equal to the frictional force. Prediction 1-1. Suppose that the cart moves with a larger constant velocity. Will the frictional force be different from before? Okay, let's go ahead and do the experiment. Same friction. I'm going to give it a push to get it started, to give it a faster velocity. Okay, now we're going to have to zoom in a little bit, but first of all, let's take a look. That last run there, what was the acceleration? Looks like the acceleration stayed 0, didn't it? And on the velocity graph, we see that the velocity remained constant until it made contact. So the velocity was 0 as well. The applied force still remained the same, 0.50. So, what do we know here? Question 1-3. Does the magnitude of the frictional force seem to depend upon the velocity of the cart? No. We got more velocity. We got the same amount of friction, didn't we? Because we got a constant acceleration. Now, let's go ahead to step number 11. Raise the friction pad a little bit so that it rubs the track more lightly. And this time we're going to see if there's going to be some acceleration. So I'm going to remove 40 grams from the box, put it in the cart so that it maintains a constant mass. Let me go ahead and pull it back here. What's going to happen? We zero the force sensor. And let's see what happens. I'm going to clear out all the runs here so we can see what happens. We have an acceleration, don't we? We have a constant acceleration. The acceleration went up, okay, or there was an acceleration. The magnitude of that acceleration looks like the magnitude of the acceleration is 0.2 meters per second squared, which is somewhat less than what we had before. The applied force is 0.47, so the applied force remains somewhat the same, but the frictional force then had to be less in order for us to have an acceleration. And we can actually calculate that. So on step number 11, the applied force to the cart was 0.47 newtons. The average acceleration is 0.2 meters per second squared. Question 1-4. You should have noted that the acceleration of the cart is noticeably less than that in steps 3 through 5. Is Newton's second law violated? The answer is no, because we have another force. We have the force of the weight pulling the cart forward, but we have a frictional force which is opposing it, going in the opposite direction. Question 1-5. Based on the measured acceleration and the mass of the cart, what should the magnitude of the combined net force on the cart be if Newton's second law is correct? So let's go ahead and go back to the whiteboard. And what we have here is we have an acceleration, or we have a force F. So the force of the tension is equal to 0.47 newtons. The force of friction we do not know. We do know that the acceleration is 0.20 meters per second squared. We also know from the previous experiment that the applied force F was 0.43 newtons, and that the acceleration A was 0.779 meters per second squared. So let's go ahead and do some calculation here. That's easy enough. We take the force 0.43, divide that by 0.779, and that gives us a mass of m is equal to half a kilogram. So call it 0.552 kilograms. Okay, now that we know that, then what we can, to find the frictional force F, all we need to do is take the applied force, or take the acceleration ma, subtract the applied force, and that will give us our frictional force. And so ma is 0.552 kilograms times 0.2 meters per second squared. We're going to subtract 0.47 newtons, and that gives us a frictional force 0.552 times 0.2 minus 0.47. That gives us a frictional force of minus 0.36 newtons. Okay. So, see how that worked out? If I take 0.36 newtons in one direction, I get a certain 0.36 newtons in one direction, 0.47 newtons in the opposite direction. With the mass that we have, we get that acceleration. And that finishes up question 1-5. Now I'm going to have a little discussion about extension 1-2 and extension 1-3 later. So at this point, we're going to go ahead and stop recording. This finishes up investigation number 1. And I'll talk about investigation 2. I'll get ready to set up with investigation 2. I'm going to need to find me a volunteer for this one. Right? Take care. I'll see you all later.